Greetings, everyone. Good morning or good afternoon, depending on what time zone you're in. We will begin the webinar here in about 5 more minutes. I just wanted to go ahead and start, get everybody situated. We'll be making introductory remarks here in just a few minutes, but we will start at the top of the hour. So thank you. Again, greetings. We're going to be starting the webinar in about another couple minutes. If you're here for the July ASBI webinar, you're in the right place. If you're here for the British Baking Show, maybe you logged into the wrong part of the internet. So we'll get started here in about another 2 minutes. All right, well, I have the top of the hour, and as my mentors always taught me, let's start on time and finish on time. So we'll go ahead and get started with today's webinar. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute. I want to welcome you to our monthly webinar. I'd encourage you to follow the American Segmental Bridge Institute on LinkedIn if you're not already. You can also follow us on Twitter, but I'd certainly encourage you to follow us on LinkedIn if you have a LinkedIn account. You also follow me, the Executive Director, Greg Freeby. We're putting up a lot of information about every few days on our LinkedIn page. Announcements about upcoming events, but also some looks back at previous projects that have been done, sort of some historical information. So a lot of good stuff, even about some learning posts coming up just about segmental bridge technology. So you might be able to, check those out. Some quick announcements before we get started with our webinar. Our August webinar is registration's already open on the website. That's August 25th, and it will be again from noon to 1 Central. And I say again, today we're going to run a little long, and I'll talk about that. The presentation will be by Jeremy Johansson with McNary Bergeron. He's going to be talking about detailing segmental concrete box girders for constructability. This is a presentation that sort of draws from a two-part series of articles he has written for the Aspire Bridge magazine. The first one came out in the current summer issue of the Aspire magazine. The second installment will come in the fall edition. If you're not subscribing to the Aspire Bridge magazine, I'd encourage you to do so. You can just Google Aspire Bridge magazine and you'll be able to find it. Another upcoming event I want you to be aware of is our 2021 convention is in Tucson at the Westin La Paloma, November 8th through 10th. This will be an in-person meeting. Great facility. We should be able to easily social distance if those requirements come back on us. But it is definitely planned as an in-person meeting with committee meetings held the day before. We start then at noon on the 8th, or at 1 o'clock on the 8th. So let's go over some quick instructions about how the webinar functions, just to make it easier. You do need to use computer audio for this session. I think most people do. We're using a recorded video, and so if you're called in on a phone, you wouldn't be able to actually hear the audio with the video, but it looks like everybody's logged in on computer audio, so that's good. If you lose your connection at any point, you can rejoin the webinar. You will miss content while you're away. We will issue certificates of attendance to folks who've completed the minimum amount of time required in the session. Today, what that means is if you've seen the entire presentation, you'll most certainly be issued a certificate. We're going to run a little long. The presentation runs about 54 minutes, and then we'll do question and answer after that. So while we are using pre-recorded presentation from our 2020 convention that Mr. John Corven did for us, but John is online with us live today, and we'll be doing a live Q&A session after the presentation goes. But having said that, you're welcome to input any questions you have while the presentation is going. Just as things come up to you, go ahead and put in those questions, and I'll talk about how to do that. And then we'll go live with John. I'll serve as moderator, and we'll do a little Q&A till about the half hour, whatever we have time for, and then we'll conclude the webinar. Again, I just mentioned it's longer than those in the past. Presentation runs around 54 minutes long, and we'll follow that with the Q&A. So this is how you interface with the GoToWebinar in order to do questions. You should have on your little pane a little questions pull down. You just click that, enter your question and hit send, and I will collect up those questions, and then I'll be serving as moderator to do them. If you're on a mobile device, you should have a question mark in the upper right hand corner. You just hit that question mark, and then a little dialog box will come up to allow you to input a question. We are meeting the requirements from RCEP for professional development hours, so we will be able to issue certificates for this live webinar. If you have a colleague that didn't make it to today's webinar, the recording will be made available. Unfortunately, we can't issue PDH certificates for viewing a recording, so that's the only stipulation. But I'd encourage you, again, if you have colleagues who missed this and you'd like for them, the video will probably be up as early as tomorrow. So with that, I'm going to go ahead and introduce the video, and our speaker is Mr. John Corven. He's the Chief Bridge Engineer of Corven Engineering. It's a Hardesty and Hanover company now. John has over 40 years of experience, is recognized as a national leader in the design and construction, engineering, inspection, and rehab of complex concrete bridges, and has special expertise in segmental and even cable-stayed bridges. John's going to share with us today a lot of what he knows about load rating of segmental bridges. He's going to talk about some of the challenges, and you'll see in the learning objectives what all he's going to cover. So with that, I'm going to go ahead and start the video. And again, this runs about 54 minutes long. John's going to be walking us through some slides and talking about the load rating process. And then after that, we'll have some time for Q&A. So with that, we'll begin the video.
Welcome to this Legacy Track presentation of the American Segmental Bridge Institute Annual Convention for 2020. The topic for today's presentation is Load Resistance Factor Rating, LRFR, of concrete segmental bridges. My name is John Corven, and I will be your presenter today. It has been a great privilege of mine to be a member of the American Segmental Bridge Institute since its inception, and a distinct privilege to be serving as a member of your executive board. The purpose of the 2020 virtual convention is listed here below, as well as learning objectives that can be taken away from this presentation. I'll let you read those on your own. Let's begin by looking into the Manual for Bridge Evaluation and consider general requirements and those specific to load rating segmental bridges. Looking at a timeline for the development of requirements for segmental bridge LRFRs, we can see that the history is fairly recent. The first attempt at trying to load rate segmental bridges with regard to a calibrated condition consistent with LRFD was prepared for the Florida Department of Transportation by Dr. Dennis Mertz and Corven Engineering in 2002. In 2003, the first edition of the Guide Manual of Condition Evaluation and Load Resistance Factor Rating of Highway Bridges was produced, but there were no segmental bridge special provisions. In 2005, the interims to the first edition of the guide specification added the segmental bridge requirements developed by the Florida Department of Transportation. In 2008, the first edition of the Manual of Bridge Evaluation, MBE, was produced, and we are currently in the third edition of that document. Now, through those years from 2002 to 2020, the Florida Department of Transportation has continued to provide supplementary information to the segmental bridge requirements in the MBE, and I would recommend highly reviewing the current version of the FDOT Load Rating Manual dated 2020. The primary purpose of including load rating requirements inside of the Manual of Bridge Evaluation was to give an approach to load rating those bridges that were designed in accordance with the AASHTO LRFD design specifications. The requirements for these kind of load ratings are provided in Chapter 6 of the MBE, and they are provided in two parts. Part A focuses solely on those LRFR requirements. Part B provides guidance for two other load rating methodologies, the allowable stress rating and the load factor rating, which would be applied to bridges of an older age. Also inside of the chapter governing load rating requirements in the MBE are sections that address bridge types by their primary material type. And then also specific bridge types are discussed as well. Inside of MBE, we have then three load rating procedures defined: designed load ratings, legal load ratings, and permit load ratings. And inside of LRFR, the quote here from the MBE, each procedure geared to a specific live load model with specially calibrated factors and a uniform and acceptable reliability. And this will be important for segmental bridges, as we'll see in this presentation. Inside of MBE, the three load rating procedures are placed into two load rating levels. The first of these, the inventory rating level, is for design loads, consistent with the design loads inside of the AASHTO LRFD manual. The definition of an inventory rating would be that level of load that can safely use a bridge for an indefinite period of time. The second level of load rating is the operating rating, where we consider design loads, legal loads, and permit loads, all three of the procedures inside of MBE, to look at the maximum load level to which the structure may be subjected. And inside of your load ratings that you might produce, not only do we have the standard vehicles produced or mentioned inside of the MBE, which are those at the federal level, but every state will have their own vehicles to look at to consider those legal loads and permit loads that have to be considered inside of these two rating levels. Now, taking these three load rating procedures that get applied to two different levels of operating ratings, we need to also think for segmental bridges of 5 principal limit states that need to be verified. Those general behaviors of the longitudinal girder and the transverse cross-section. We need to look at the flexural strength of those elements, as well as the service level stresses in compression and tension. We need to think about the ultimate or strength shear conditions, as well as the principal tensile stresses in service conditions. The result is a lot of numbers. Again, 3 load rating procedures, 2 rating levels, 5 limit states, all of these typically performed at each joint between each precast segment in a bridge. Consider this project in Birmingham, Alabama, recently completed I-20 and I-59 through the Central Business District. It's about 1 million square feet of segmental bridges, complicated by the fact of having eastbound and westbound bridges that are joined with longitudinal closure strips. So in this particular case, there were 14 different load conditions or vehicles that needed to be load rated. Design plus legal loads for the state plus their permit loads. We looked at the 5 different load effects that needed to be analyzed, and then the number of segments for this job, 2,316, generated a total number of rating factors for this project in excess of 162,000. Now, I say in excess not just because of the extra 120, but because you also have to think about the transverse placement of loads to produce critical effects here specifically because the bridge is made of multiple girders joined together. And so we needed to think about load distribution factors and how torsion related to longitudinal shears, to longitudinal flexure, and it's a bunch of numbers. But fortunately, through the computational efforts or methods that we have analytically, plus good spreadsheets, the numbers are processed fairly quickly, and we can do the appropriate searches for the controlling load ratings. As someone begins to tackle a load rating for a segmental bridge, they should understand that it's going to be a complex process. And the reason why, it's the same reasons that they are complex to design. The state of permanent stress inside of the bridge is dependent on the construction method and also then the sequence of construction within that method. The state of permanent stresses is a function not only of all the built-in forces in methodology and sequence, but also because of the time-dependent nature of the concrete and pre-stressing steel. There is a complexity added, and we will address this towards the end of the presentation, because we are so heavily dependent in load ratings for segmental bridges on service limit states, keeping joints appropriately pre-compressed. And the fact that we have an incomplete calibration at these service limit states means that we have to do a lot of interpretation of the results on behalf of our owners. Before moving on to the specifics of load rating segmental bridges by LRFR methodologies, it will be helpful to review the calibration efforts that were undertaken by the AASHTO community in developing the LRFD specifications, as well as the LRFR manual itself. The calibration of the LRFD design specification was prepared on a probabilistic basis, where resistances were established with appropriate reduction factors and loads were set with appropriate load factors in such a way that there would be a very low probability of loads factored exceeding reduced resistances. The basic equation we're striving for at AASHTO is that those reduced resistances are always greater than the summation of all the loads acting. When the work was done, it was considered that both loads and resistances were normalized random variables, and so we produced normalized random variable curves to represent the distribution of probability of those two features. And because they are considered as normal random variables, we can use relationships to compute the standard deviation of the difference between the two probabilistic curves, resistance and load. Now normally these would be, in their normalized form, centered with the mean about the vertical axis here shown on the left with a value of 0. But by using and introducing another variable, beta, or the reliability index, we can use multiples of the standard deviation to shift the probabilistic curve to the right to an extent that the probability of failing the design criteria would be very small. And that level of failure or amount of failure is expressed by the area under the probabilistic curve to the left of the vertical axis on this slide. And so for design, those at the AASHTO community proposed and have incorporated a reliability index, a shift from the normal vertical axis there to the right of 3.5 standard deviations of the differential information. And then proposed and introduced inside of the MBE, there is a reliability index of 2.5. So in the design portion of the code, which would also be at the inventory level ratings, we're looking at a lower probability of failure of the design criteria. Also, then for the operating rating conditions, we're looking for the possibility of slightly higher percentages of failure. And you can see the percentages under a normal curve of normal bell-shaped curve, if that were to be the case for the load effect being studied, that the failure using a beta of 3.5 standard deviations would only represent a 0.02% of the cases, whereas in the inventory condition, or the operating condition, sorry, it would be 0.62%. And so it's important to understand that these failure probabilities, however, are knowing that we have factors on loads and reductions of capacity. So it does give us a very, very robust and reliable code. Just final thoughts on that, and where it boils down to some information on segmental bridges, is that there was then the work by the AASHTO community to produce that set of load factors and capacity reduction factors, or capacity factors, to establish the two levels, one for design and one for load rating. This work, however, was done only at strength limit states to produce reliabilities consistent between the old AASHTO standard specifications and the new, now somewhat old, AASHTO LRFD specifications. There was no calibration prepared or developed or analyzed or produced for service conditions or fatigue and fracture limit states. These were solely chosen, the load factors, as we moved into LRFD, so that materials, or members rather, member proportions produced under the new code would be comparable to those found in the standard specifications. This is a good example of this would be the 0.8 factor used for the service 3 condition when checking tensile stresses in pre-stressed beams. That value is there just to make sure that in the service conditions those beams were no larger or no greater pre-stressing requirement than that produced in the standard specification. So it leaves us with the fact that the LRFR, for the work we're trying to do for our clients, has no service load calibration, and this has great impact on how we prepare an LRFR. Let's go back now and consider those things necessary to produce a load rating for a segmental bridge under the LRFR methodology. The first of those is data collection. And this would be the case for any older bridge that you're going to be looking at. But we do know that there is a lot of information produced during the design for segmental bridges. There are obviously the design plans and then hopefully a well put together set of as-builts, but construction documents, whether they be proposed contractor modifications, all of the segment shop drawings, post-tensioning system shop drawings, and if they're kept well in their records, the casting and erection manuals are all information that can be used to populate the analysis and rating of the bridges. We need to look at well-kept maintenance inspection reports, and also anything that has been done to repair or rehabilitate the bridge since it was open to traffic. And then finally, field surveys and measurement. If it's of such a condition that takes someone to go out and look at it, then by all means that should be a part of the data collection process. Looking at some of the specific information we hope to find when getting ready to prepare a LRFR for a segmental bridge are things like the casting and erection dates of the precast segments. And this might only be found in some cases after scouring through field logs. Concrete strengths can become important if we are trying to project forward additional capacity given the age of the bridge today. The mechanics of the erection process, when spans were closed, when temporary supports were moved, how was fixity at piers and towers placed, and when were they released, how were erection loads moved, gantries, counterweights, and those things. How large were these loads and where were they positioned in the spans? Information regarding the post-tensioning stressing dates obviously would be of great benefit to building the time-dependent construction analysis, which will follow up in the next session here. And then finally, the types of ducts used in the project so that the mechanical information of the PT system can be found. And then finally, the current condition of the structural components. This may require, again, a site visit to see if the evaluation given is as stated in the most recent bridge inspection reports. Let's move and just take a look at material properties needed to get moving in the LRFR. And there are really three that we're looking at. We're looking at the concrete strength and density. Um, again, wanting to be able to, if necessary, incorporate actual as cast concrete features. If modulus of elasticity values were found during construction through lab testing, it'd be nice to use those specifically. And then the creep, shrinkage, and thermal characteristics of that concrete. If we, for example, can't find these things, then we would have to rely back on code supplied values with the understanding of how they might impact the load rating. For the pre-stressing steel, modulus of elasticity typically found through the testing required in the specifications, but also the relaxation characteristics and capacities, both at yield and ultimate strength. And again, as we just mentioned, those features of the jacking process, the mechanical properties, friction, wobble, and anchor set. Having gathered all the data we need to support the load rating process and establishing the material characteristics that will be used for the load ratings, we can move on to the types of analyses that need to be performed. The first will be in the longitudinal direction of the girder, or that dealing with the global flexure and shear of the box girder. To do that, we'll use either a 2- or 3-dimensional structural analysis piece of software, depending on the horizontal curvature of the bridge. There are many good products out there for use that allow us to prepare time-dependent, step-by-step construction analyses so that we can capture all the locked-in erection loads and erection sequences found in the data during our data collection phase. We can then run the bridge analyses out to a time to the current day in the life of the bridge so that we can establish the creep and shrinkage effects that have taken place so far. Also, then, that software will allow us to account for all the post-tensioning effects, the primary flexural effects, secondary bending moments because of continuity, and then the losses due to instantaneous friction, wobble, elastic shortening, and anchor set, but also those associated with long-term effects of the pre-stressing steel with regard to relaxation, and also consistent with the shortening of the bridge because of the creep and shrinkage of the concrete. As an example of the look and depth of analysis, this is a fairly short segmental bridge in Tennessee, bridge number 2 on the Foothills Parkway, but a highly curved structure with a minimum radius there to the right of about 262 feet and super elevations that varied back and forth considerably. Span lengths are about 180 feet, and the girder depth is, I believe it's 10 feet deep. And for this analyses, we prepared 3-dimensional time-dependent construction analyses where we exactly replicated the contractor's method of construction, all the post-tensioning details, and led to a very effective accumulation of all the permanent conditions or the permanent state of stress within the bridge. The second analytical requirement is going to be in the transverse direction of the box girder. Now, traditionally, we have used a combination of influence surfaces or very simple fixed-end finite element analyses to produce localized moments for concentrated loads. And then taking those concentrated loads, distributing them on a 2-dimensional frame, and then superimposing to sum all the moments. If there is something more complicated like a combined girder cross-section, there are other simplified methods such as Fouchard's method that can be used to determine the distribution of load between multiple girders and the generalized effect of bending within a span. Now, there might be the case when something more significant needs to be done. Either we need to avoid a posting of a bridge, or the cross-section is so complex that the traditional methods don't apply. And in that case, there will be the need to move to more complete finite element modeling. There is some caution to be taken here, that we don't get too caught up in finding absolute minimums and absolute maximums, because typically there are certain controlling features. For example, you have a cantilever live load moment at midspan that might be distributed longitudinally along the length of the girder as per the deflection of the span, but back at the pier where there's no deflection, that load is still very concentrated. So we want to be sure and use the most dominant governing number there. And this shows that more traditional approach. We have uniform loads like the self-weight, wearing surface, and barrier rails that can be applied to our computerized model. We transform from the typical model to idealized members to the computer model. And those things that happen per foot we can apply directly to the model. And then in the bottom left-hand corner you see the application, in this case, of two HS-20 trucks in a position such as to produce, I think it's negative maximum positive bending actually here between the webs. And we would perform that on either a influence surface in finite element or finite element program, and then distribute those things around the very simple frame, and then work to sum the moments to finish that analysis. With analytical computational efforts behind us, we can then move on to the rating equation itself to find rating factors. And we find from the MBE equation 6A42.1-1 a very simple expression of capacity C minus load effects, which can be plus or minus in the last aspect there, the permanent loads, divided by the unit of live load that is going to be considered for that particular vehicle. So rating factor equals capacity minus those things that have already been working towards reducing the capacity divided by the live load. The two shown here, the self-weight of the segments plus other superimposed loads, are known to be reducing, but in the permanent loads there are those that could be additive. At midspan of a segmental bridge there might be, or let's say at the pier of a segmental bridge, where the secondary moments are reducing overall negative moments, so that would actually be adding to capacity through a positive sign here. So we want to make sure that we track all the right sign conventions of all the different loads that we are including in the rating factor computation. When we think about the capacity of the bridge, however, we want to be sure that we recognize that MBE has produced factors, and I guess it's in LRFD as well, but we have condition factors based on the condition of the bridge, and those parameters of what that factor would be are given inside of the MBE. A system factor, which is something that is very understandable within highly redundant structures, but there are special conditions within inside segmental bridges that need to be thought about there. And then you have the LRFD resistance factors that are normally placed on the type of member being verified. Those system factors we talked about, that we need to give appropriate consideration to the robustness of segmental bridges in their typical condition of longitudinal continuity. A big one here, the continuum of the box girder, the fact of the torsionally stiff section and its extremely robust nature with regard to carrying load and distributing through multiple tendon load paths given throughout the section. The number of webs gives us another feature with regard to load paths, and then the post-tensioning details themselves can play into the system factor. I've included here the table for system factors found inside the MBE, just to show how these things can vary given the type of structure, the type of the span and how it is or is not continuous, and then the type of post-tensioning as typically applied by the method of construction. The exercise was normalized for an interior span of a 2-web box with span by span or typically external post-tensioning. And then other factors were taken from there, and this was done and originally prepared in a sensitivity analysis by Dr. Dennis Mertz. An interesting expansion of the load rating equation found in the MBE is the segmental equation given by the Florida Department of Transportation in their load rating manual. It calls to our attention the need to include all the loads that are appropriate for service limit state verifications and load ratings. Often there might be a bridge type that is only being load rated at strength limit states, where some of these loads have been dissipated through hinging or redistribution mechanisms. But we need to be sure and apply all of the appropriate load factors at service limit states, load demands rather, at service limit states. Having considered the expanded form of the load rating equation, we can then begin to gather the factors, the capacity factors and the load factors, in order to modify the results from our analyses to produce the rating factors. The first level of rating, the inventory rating, I won't look at too much detail here because it's all pretty much as per the AASHTO LRFD code. Key at the inventory level that whether we do strength or service loads, the second and third bullet under the live loads there, we are using the number of design lanes. And also we should be including thermal gradient in the inventory ratings at service limit states only and not at the strength limit states. Presented on this slide are those similar features for operating ratings of a segmental bridge. Permanent loads, again, as with inventory ratings, pretty much consistent with AASHTO LRFD. When we get to live loads, we do notice the difference in the second and third bullets, that at strength limit states we're looking at the number of design lanes, but at the service limit states we're looking at the number of stripe lanes. This is being done because the calibration that was produced to make the LRFR was done at strength limit states, so we know that and have confidence in those load factors. But there was a fixed prepared by Dr. Mertz and Corven Engineering that introduced this concept of striped lanes based on the work done with the Florida Department of Transportation back in 2002. And so that allowed a level of calibration at the service limit state that wasn't appreciated before that. The other interesting load feature is that at the bottom there we see that there is no thermal gradient in any condition, strength or service limit state, for an operating rating of a segmental bridge. And so I mentioned before that there are 3 loading procedures, 2 load rating levels, and 5 limit states. The one that is interesting to consider is that of the principal tension stress. To determine the principal tension rating factors, we look at Moore's circle for a cross section. We know the features of the bridge design. In this case, there is no vertical compressive stress, so that we only have to deal with the axial stress, P over A or F over A, sigma 1, and the computed shear stress at the neutral axis will allow us then to find the radius of the Moore's circle. And also we can locate the circle center as just being half of the axial force, as there is no vertical compression in this particular case, no vertical post-tensioning in the webs. That allows us to then find a minimum stress or minimum principal stress at the under the permanent conditions. We then apply live load, and we have really no change in axial force, but we do have an additional shear stress that's being applied. Now, if there are a haunched bridge or variable depth bridge, there might be an additional axial force produced by the vertical loads, and that would have to be considered as well. But for this constant depth bridge, we just would be adding a change in shear force, which would then enlarge the Mohr circle, creating a larger principal tension. And we can look at the difference in those two principal tensions, sigma min and sigma min prime, and compute delta sigma min, and that would be the change in the principal tension for the given live load effect, and the multiples of delta sigma between the minimum stress under permanent loads and the absolute minimum given by the criteria would then give us our rating factor. We'll look at an example real quick. Under construction right down in Miami is I-395 being built by the joint venture of Archer Weston and DeMoya. And in that bridge, we were able to produce a fairly robust principal tension because we're using some large draped external continuity tendons. In this particular bridge, it's built in balanced cantilever with span lengths of typically 225 feet. And this example, looking at of the multiple roadway widths there, this is a 40-foot roadway, the structure depth 10 feet, and the total of two webs 2.5 feet thick. And we can see that the stress produced as P over A being the 178.9 KSF, the dead load shear stress, or not dead load, but permanent stress, dead load minus the pre-stressing and all other load effects. And then we find in this particular case, this was the rating for HS20, for the HL93 load, the additional shear stress produced by that load. And we found the two principal tensile stresses for those two conditions, with the difference being 9.2 KSF in additional tension. And so we know the limit in Florida here would be 3.5 square root F prime sub C. We're using a concrete strain of 8,000 psi. So looking at the rating factor equation, the capacity would be that tensile limit, 3 times the square root. We would be subtracting from that the demand that's there, the permanent state of principal tension of 11.35, and dividing by the variable of a unit load or a unit value of the influences of HL93, and see a fairly large rating factor of 3.67 for this bridge, which we're very happy to have. Allowable stresses, we mentioned for in Florida, the principal tension here towards the bottom of the page, you'll find the principal, the allowable stresses based on concrete strength, multiples of concrete strength at both the inventory and operating rating. This table is interesting. It's taken from the Florida DOT load rating manual, and it gives slightly more guidance than those stresses that are offered in the LRFD. The LRFD allowable stresses would be those that the load rating, the LRFR requirements inside of the manual for bridge evaluation would push you to. So if additional information or background might be needed on allowable stresses, look to the Florida DOT load rating manual. And so we put together all those things. We put together the data that we need to collect, gather together and define the material characteristics. We perform the analyses necessary, longitudinal construction analysis, transverse features of the box girder analysis, and then we apply the rating factors with the appropriate, or the rating equation with the appropriate factors, and we produce segmental bridge load ratings. But unfortunately, there still are some difficulties that are encountered and that need to be discussed well inside your load rating team and also with the owner to establish appropriate expectations. Let's take a look at some of those difficulties that you might run into when you prepare an LRFR for a segmental bridge. First of all, you might be tasked with load rating a bridge, an older bridge, that was designed in accordance with the AASHTO standard specifications, as opposed to the now applicable AASHTO LRFD specifications. Changes in live load models, as well as other loads like the way we compute thermal gradient, can lead to a likely condition that the bridge will not rate at LRFR levels under the inventory load ratings or design level load ratings. These inventory ratings are very important to the way DOTs operate, and this information should be explained thoroughly and with your client. In the day of AASHTO standard specifications, there was no principal stress requirement. Engineers did on their own sometimes consider principal stress, and that would be a good thing, but you may not necessarily have had that incorporated in the design. And so you may need to accept a higher stress limit as opposed to 3.5 square root to 4 or 4.5 square root if the bridge is operating currently without any web cracking. There has been changes in shear design provisions for the capacity side of the rating equation for shear between standard specifications and LRFD, going back to BCI, BCW, and a variable Craig angle method, traditional method for accounting for segmental bridge shear capacity. Now it's modified compression field theory, strut and tie analogies, and a fixed angle approach to the traditional segmental methodology. These two together are very important because we don't want to have an inappropriate distance between our principal stress ratings and our shear strength ratings. The calibration of live load at service limit states is not in place at this point, and we don't want to over predict a load rating factor that might lend itself towards creeping towards or moving towards the limits of a brittle shear failure. One of the bigger issues we find often is running into limited as-built information, plans, shop drawings, direction manuals, and it's can be really kind of barren when you go to try to find that information. And so to get around that, we often have to prepare enveloping ratings, where we consider that set of conditions that might enhance the load rating of young segments produced in a very rapid sequence of construction to produce the most creep redistribution and what would traditionally be the positive flexural sides in load rating. And then also to look at historical averages for segmental bridges and a slow erection sequence down, and to add age to the precast segments when they're erected to produce another end that might lead to a lesser estimation of creep redistribution, which would leave a more taxing condition at the piers in negative bending. And so that's often a strategy that's used when information is not available. One that we have encountered recently is that standard bridge inspections don't always accurately assess the condition of a post-tensioning system. Inspections of post-tension segmental bridges are more complicated than normal, and many inspectors are not or have not had the opportunity to be trained to look for specific issues that might affect the condition of a post-tensioning system. And so it might be wise to visit the site and audit the condition of the bridge before preparing the load rating. When we look at service limit stresses, and whether in the direct tensile side and the principal stress side, the rating equation numerators are usually very small, as the bridges were designed typically right up to the limit of zero stress in the joints. in the longitudinal direction, or right to the limit of a fairly small stress, 3.5 square root for principal tension. The result is that small changes in capacities or in the demand side can greatly fluctuate the changes in the load rating results. So it may be that it is important to perform somewhat of a sensitivity analysis on those features before recommending an appropriate factor to your client. Another difficulty that can come, or an opportunity, is the fact that there needs to be a hard look at the concurrency of the load conditions for longitudinal and transverse load ratings to not over penalize, but then on the other side also overestimate load rating capacities if in fact they do act concurrently. And then finally, there is a great deal of difficulty sometime in dealing with owners' expectations. The normal costs and schedules for load ratings are fairly well known, but for segmental bridges the costs are higher and it takes longer to prepare load ratings, and so we need to effectively explain all these nuances to our owners. I've made a lot during this, or at least implied a lot about the lack of calibration of service limit states in the current LRFR criteria, and looking at a few ratios here to understand where the calibration that does exist came from. That the expression of lane loads comes from the fact that back in 2002 we looked at the majority of Florida segmental bridges, and they were typically on the order of 40 foot in width of roadway that were striped for 2 lanes and designed for 3. And so when we look through the strength limit state factors provided by AASHTO and the MBE, the 1.75 and the 1.35, we compute essentially an effective number of lanes, and we find the operating to inventory ratio, the 0.77, as a factor really that's, track it back there to the left-hand side of the equation, it's the ratio of 1.35 over 1.75. When you looked at service limit states for this condition, and you looked at the stripe lanes and the change in multi-presence factor, we were able to produce a ratio of operating to inventory at service limit states of about 0.8, and we were very pleased with that. And we saw that additionally that the strength to service ratios of inventory and operating ratings were right on top of each other, the 2.19 and the 2.15. So we felt that the number of design lanes with the appropriate multi-presence factor was a good fit for calibrating the live loads for a operating condition in an LRFR. We recognized, however, that the calibration offered by the number of striped lanes has difficulties when bridge widths change. Going through the same exercise for a 56-foot roadway that is designed for 4 lanes and striped for 3, we run through the same math, and we still find at strength limit states the ratio of the 2 load factors, the 0.77. We then go down to service limit states and we apply 3 striped lanes and a multi-presence factor that is consistent with that, and we find the ratio of operating to inventory at service limit states is 0.98. When we then look at the resulting ratio between inventory and at strength and service limit states, we're still at 2.19, but we've reduced the ratio strength to service at the operating condition. And this is a reflection then that the higher ratio of operating to inventory at service limit states is a reflection that the bridge is being rated at operating levels with too much live load, and the owner is not recognizing as much capacity as he could have. Likewise, when we go to a smaller roadway, a very typical roadway width of 26 feet with 2 design lanes and 1 stripe lane, again, at strength limit states, we have the same calibration. At service limit states, we follow through and we find the reduction in the ratio of operating to inventory service stress to 0.6, which means that we don't have enough live load on the bridge at inventory level if we follow the striped lane rules. And so when you move into widths different from the condition of 3 design lanes and 2 stripe lanes, there needs to be some cognizance of adjusting the live load results at operating levels in order to not overestimate or underestimate the load rating results, which can put you in a real pickle, and it just needs a lot of interpretation on your part. Fortunately, though not immediately available to us, through the direction of Jeff Pouliot, who is at the Florida Department of Transportation and help runs our maintenance subcommittee with regard to segmental bridges inside of ASBI, we have been able to move forward to NCHRP, a new study that will be commissioned soon, in which we are moving towards having the service limit states calibrated, along with good examples to allow us to pass that information along. So there will be relief in the future for some modification of the striped lane theory from these results. But in the meantime, it still takes a little bit of nuanced touch to get the right separation and the right level of load at operating levels. But it's a lot of information, and just a couple last thoughts. Don't forget that recently, fairly recently, we have 2 new federally provided requirements for emergency vehicles, the EV2 and the EV3 vehicles. You may have been asked to go back and include these in load ratings that you've already prepared for owners. And then also, though maybe not really a load rating, but someone might ask you to evaluate at a LRFD level a transit structure, which segmental bridges and transit structures go well together. And so don't get caught in applying the calibrated effects between the standard specifications or whatever design code the system was designed for, its load factors. Don't get caught in the calibration changes. These are fixed transit loads, and so they're not a notional load that's been adjusted inside of the framework of the design. So though you may advance other factors of the LRFR in evaluating the bridge, the live load factor should definitely remain as the original design. Well, thanks for listening today, and hopefully this will advance your capability in preparing load ratings for segmental bridges under the Manual Bridge Evaluation load rating requirements. And take a look and note the code word. Note the code word.
All right, everybody. So let me hop over here. Actually, I wasn't going to start webcam. So we have some time for question and answer, and we had a few that came in during the webinar, and we'll cover those. We also had one that came in prior to the webinar that I'd like to share with the group and get John's response. And so I'll read it. The question is, according to the Manual for Bridge Evaluation, Table 6A.4.2.2-1 and Sections 6A 5.4.2.2a and 6A 5.11.5.2, checking longitudinal tension, which is service 3, is required for segmental bridges, but not for other pre-stressed concrete bridge types. Why is that, particularly for cast in place segmental, which has bonded mild steel across the joints? So John?
Okay, that's a pass to me. Thanks. Hey, folks. I'm going to actually bring up the response that I had sent with that. So bear with me 1 second. I go to send items, and I think that obviously a great question. I'm just going to read my response there. The developers of the MBE felt comfortable that the service limit states for pre-stressed beams designed in accordance with LRFD provisions, loads, distribution factors, load factors, etc., were sufficiently calibrated such that load ratings performed at strength limit states would be consistent with load ratings at service limit states. They did not have that confidence when it came to service conditions with segmental bridges, with or without bonded reinforcing. The Band-Aid that was offered, or the fix by Dennis Mertz and others, was to introduce this idea of stripe lanes so that the service limit state ratings would not routinely govern segmental bridge load ratings. Unfortunately, that as you just saw in the presentation, that was only common for or developed for a bridge 3 design lanes and 2 that are striped, and other configurations they don't work as appropriate. Therefore, the MBE left the requirements in to stress or to check the service limit states. So I guess the short of it is that the calibration was such that if you did a strength limit state on a beam, the owner knew that he would also get a very similar rating at the service limit states, so they are not necessarily wanting to pay for the work, the effort into preparing something they know that would not necessarily govern. And that's where the MBE lighted on that regard. So I think it's a smart move on their part. And if we ever get a calibration like that for segmental, maybe that would reduce the load, the effort as well on behalf of our owners.
All right, thank you, John. Well, I will then, I'll walk us through some of the questions that came in during the webinar, and I may even help field this first one. So the first question is, the beta factor that was established would have been established based on a design life for 75 years. Has guidance been provided, or has any owner tried to address the reduced beta factor when extending the service life to 125 or 150 years? And I will say, my part, the answer to this question is on the AASHTO front. AASHTO did create a guide specification for service life design of highway bridges. And so there are recommendations in that publication about how one would go about designing for an extended service life. But John, do you have any additional thoughts on that?
Yeah, I think this is a great question, especially for folks who get into more exotic structure types and more important structures that owners are really putting out these days. I have to tell you, most of the times when we see extended service life requirements in an RFP, the response ends up being better materials or more aggressive specifications to control quality, and not so often adjusting the loads to account for a reliability that might be consistent with a load level in the future, or one that considers or captures an occurrence of load within a greater period of time. So it's a fantastic question. I do not know necessarily of anybody who's done anything across the board in this area, but if I were an owner, I would want to know 2 things. Yes, you're going to give me better materials that are going to last longer, but I'd also want to know that you captured loads that are going to be out there during the design life of the bridge, which could be bigger than the 75-year period. So I think it is really incumbent upon the owner to ask for it and engineers to give it. In the little bit of playing that we have done with that, it doesn't take much with regard to a beta factor to move from 75 years to 125 or 150 years. The rogue vehicles that might be brought into the environment of the probabilistic evaluation are not that significant or that much more significant, or they wouldn't be out there running around, with some regularity. So it's they're small tweaks, but I think they're important tweaks. That's a great question.
All right, thank you, John. Earlier in the presentation, you were talking about load distribution, and you made a reference to a traditional distribution factor, is that the same as the approximate distribution factor from AASHTO LRFD?
Yeah, I guess you gotta be careful with words. No, traditional in that sense does not mean the distribution factors in the code that are meant for the cross sections that are shown in that portion of the code. So apologize for that word traditional, not lining that up with the AASHTO code. Really, the traditional there was the sense of traditionally segmental. So looking back in the history, we've seen other methodologies in order to define the load distributions that take a little bit more work because of the nature of the open cell, the flexible webs, bottom slab, top slabs, and the connectivity between the long cantilevers. So it's that I apologize for that
Right,
confusion.
not a problem. That's why we have the opportunity for some clarification. And there was another question. This is kind of a broad question, and I think you've covered this to a certain extent, but I'll give you an opportunity to expand a little more if you'd like. Can you explain what our principal tension stress we need to check on segmental bridges? And I know you got into the principal tensile check in quite a bit of detail. I didn't know if you wanted to add to that and maybe even provide a little bit of your own history of where that came from.
You mean bridges we've designed that have cracked? Thanks, Greg. No, I'm teasing. So we are looking for principal tensions, but it's a very fundamental check at the neutral axis in areas of high shear. So they're not necessarily, we're not checking principal tension issues at midspan where we know those things won't be large. But we do find it to be important, or have found to be important, because the behavior of webs that might be cracked because of high service stresses and their performance on load carrying capacity and the prediction of rating factors might affect that, the crack structure versus the uncracked structure, and then how it goes to a strength limit state too, and does that all still remain valid. So because of that, that along with the very non-ductile thought of shear failure, the AASHTO community in general thought it was wise to embrace a verification that we keep those things at principal tension very small. We have had instances of around the country where we do have principal tension cracks. And they are important. Owners, if you're online, you've probably injected some of those things. And so we just think it's we, being everybody in the community rather, believe it's an important thing to do to assure appropriate elastic behavior during the functioning of service limit states.
That's right. That's good, John. And I will add the most recent edition of the AASHTO LRFD, the AASHTO Concrete Design Committee elected to expand that check to apply not only to segmental structures, but also other structure types. And there's been a little pushback in the community about that. And the answer as to why T10 did that, and I say this with knowledge because I was on the committee at the time, we're pushing the limits now of our materials like never before, with taller, more slender girders, narrower webs. Stability is starting to become a big issue with some of these long, slender girders, not just segmental. And so the committee felt like, while we've not had principal tension problems historically, why wait until it's a problem, particularly as we start pushing, I'll say, the envelope on some of these fairly almost exotic girders. And so that's why that check has been expanded to apply to other structure types. It'll probably seldom control in more modest structures, particularly talking about eye girder structures, but you start getting into some really deep girders with narrow, fairly thin webs, you may find that check does start to actually control. So the next question, there's actually two questions and they're kind of related, and they have to do with the time of when the time assumptions associated with the load rating of the segmental. And so I'll start with the first one and then we'll go to the second one. Again, understand they're related. So the first is, do we rate segmental bridge? Do we do the ratings for the T equals 0 days or T equals 10,000 days, or is it both?
Yeah. And I can see that the other question coming up here. So let's start off with, say you are now doing a load rating as a requirement of your original design effort. We in Florida, that's a requirement that you have to prepare a load rating. That load rating, and again, this is owner dependent, is absent any as-built information. Obviously, nothing's gone to work there, though. Florida requires that we do that at day 10,000. The belief in the long-term condition of that. Now, if we usually have the privilege of then continuing our effort during the shop drawing review process of the project, and then rerunning the load rating at the end of construction. The bridge you're looking at in Birmingham, we've just now turning in the completed as-built load rating information to them, which was slightly different. So we had to justify to the owner that his vehicles were appropriately considered for a design state. He didn't want to pay us for 0 and 10,000. We picked the 10,000 as the norm in this particular state. And then we come back later on, given that privilege to do it at the end of construction, so that he can then go into the future with a baseline load rating. If you are doing a load rating, well, maybe Greg, maybe go on to the next question.
Yeah, I guess we can kind of segue then to the next question, because the next question again was related, and I won't tell you what, I won't even attempt to paraphrase it. I'll just go ahead and read the question as provided, and then we'll go from there. So it said, for baseline load rating for new construction, are segment ages and construction timeline assumed, i.e. provide load rating prior to construction is complete, or is the load rating done after construction is complete using known ages and timelines? If done with known ages and timelines, does it have a meaningful impact on the load rating? So there's, again, you've kind of already touched on that, but maybe even touch a little more about what do you do when you don't have those, in other words,
Right.
You don't have the luxury of being the guy who not only designed it, but also load rated it.
Yeah. So let's stick back with this, with the design that is embedded in this question here. If your envisioned direction scheme came off exactly as with just the adjustment for times and segment ages, and they were generally close, and the contractor did not in any way deviate from your erection methodology, then I would say the impacts could be small. But I don't know as that's ever happened. And I'm not so much about the segment ages at that point as any changes to the erection, the closure sequences, that the change in built-in forces. So yeah, I think the idea of championing for a post-construction load rating with the as-built information is really key. Greg did mention or imply one other thing. If you are called into load rate an old bridge, then where you do not have information, you may just have a set of design plans and all the construction records are just not available. Then there is that idea of bracketing that I think I mentioned in the presentation, of a young age and an old age construction assumptions, so that you might find what the variations are as a result of that. And usually that's just, if you've got your spreadsheet set up, you're making 2 different time dependent runs and you're exporting permanent conditions, and the rest of the numbers flow through pretty quickly and not a horrible expense to the owner. Anyway, and I think that's probably as far as that needs to go.
All right. I'm also was gonna mention, and so John, I know you're on the team for the NCHRP panel, and I won't ask you to say or anything because I know there's things you can't share, right?
Yeah.
As the project is underway.
Yes.
But I would ask you, can you at least share kind of what the sort of timeline is for when how the project's going to progress, if ballpark?
It's if you all have been involved in NCHRP process, that these can be somewhat lengthy processes, that a lot of different important reviews to be sure that the product is appropriate, and then finally introduction to the AASHTO community and stuff. We're still looking that the recommendations that would come from this are probably still between 30 and 36. Well, now it's down a little bit, but about 30 months away, 2.5 to nearly 3 years out. So it is a lengthy process, and this bridge in between now and then with regard to band-aids on load calibration is, sadly, I think it's with us for a little bit longer. But I do believe when I've seen the way the work has started, that the team's going to really produce some great information. So anyway, just look forward to that in the future, and then hopefully the AASHTO folks will embrace it quickly and codify it, and MBE as well.
Right, it's sort of a stay tuned, right?
It is.
So the other thing I wanted to share, and I just popped it up in the chat. I mentioned earlier, I think I mentioned earlier, Aspire Bridge Magazine for the presentation that Jeremy Johansson will be doing for us in August. But John also wrote an article for Aspire Magazine about load rating segmental. It was in the, not the current issue, but the previous issue, I believe, or was it in the current issue? I've lost track.
I think it's
Either
previous.
way. There's a link to it there in the chat. If you happen to, you should be able to copy it out of the chat and then paste it in your browser. Or you can always, again, Google Aspire, and I think John Corven's name, and I think it'll come up. Having said that, we do have one more question that came in while we were talking here, and I want to share that question then with John, and then we'll probably be close to wrapping up. So. We have seen some rating for design. We have seen some rating for design with inventory rating factor of 1. Per as-built condition, this rating could be under 1. Wouldn't you recommend a rating factor of greater than 1 during design?
It's a really great question. You know, so segmental bridge history is you know, we're the latecomers, and we're in the 70s and 80s trying to put together a competitive bridge with other types. And for that period of time where anything over 10 million in construction had alternate designs, there was obviously the push to make designs as efficient as possible. But if for you all on the line who are experienced at doing this, you know that to boost a load rating from a 1 to a 1.1 with regard to post-tensioning at the moment of design is not significantly a significant cost to a project. It's not, doesn't reflect 10% increase in project cost, maybe a few more strands in your continuity tenons. So I would, yes, the answer to this is that we should, where we're obviously meeting codes, and but it doesn't mean we also want our owners to, number one, be able to load rate the bridge 20 years out with a condition factor of 0.9, say, if that's what you were applying for a reduction in the theoretical numbers. But also changes in live load. Why saddle an owner with a bridge that can't live a good life in the future? However, remember that the 1.0 numbers are talking about not meeting criteria that are robust, I guess. I use that word robust a lot. Sorry about that. But there are. It doesn't mean that you're under 1 that the bridge has calamity. It just means your criteria are being exceeded. So I don't get too bugged about it. If we all of a sudden are asked to load rate a bridge where a designer kept it tight, you know, we just explain to the owner what's what, and he makes his decisions on whether he has to post or not, or strengthen. But on the other hand, if you've got the ability to do it, I know your owners find it to be nice to have a little extra capacity.
Right. Yep. That's good, John. The last question we just had was, how do we register for the the next month webinar? And I just dropped a link in the chat to that website as well. You can go at any time. The August webinar is already up. You can register for it. With that, I don't believe we have any more questions that have come up. I don't mind wrapping up a little bit before the bottom of the hour. We knew we'd run a little bit long today, but hadn't really anticipated we'd take the whole time. So with that, I will say thank you, John. We appreciate you in the segmental bridge industry. You've been an immense resource for so many years. I look forward to you actually moving up within the ASBI leadership to the president role here in another year, I guess it is.
I hear with that, and 50 cents you get a cup of coffee.
Right, exactly. So, but no, I appreciate you being not only a resource just in terms of mentoring the community, but also a technical resource to the community at large, and taking the time to put together this presentation and spending some time today with us with the Q&A. So with that, I will close the webinar. One last reminder, I don't know that I mentioned it, I think it was in my slides. We will send out certificates for attendees. Give us about, it shouldn't take a week, but if a week goes by and you haven't seen it, then pop us an email and let me know that you didn't get your certificate, but you should get it certainly within a week's time. So with that, we'll close the webinar. And again, thank you everybody and have a good day.
Thank you.